Okay, in this video we're going to cover our section 6.2 material on orthogonal sets. So let's start by defining an orthogonal set. We would say any set of vectors u1 through up in Rn is said to be an orthogonal set if each pair of distinct vectors from that set is orthogonal. So that is if the dot product of any two distinct vectors, ui and uj, is equal to 0, so that those two vectors are orthogonal whenever I is distinct from j. So as an example of this, we're asked to determine whether the set of vectors u1, u2, u3 is an orthogonal set where we're given u1, u2, and u3. So to determine if this is an orthogonal set, we need to see if any pair of vectors, any pair of distinct vectors, is orthogonal. So let's consider the dot product of u1 and u2 to start. So recall the dot product is defined as the sum of the product of the entries of these two vectors. So we would start with 0, then plus a negative 2, then plus a positive 2, which is 0. Now taking the dot product of u1 and u3, we would have a negative 5 plus 4 plus 1, which is 0. And then our last pair of vectors would be u2 and u3. So taking the dot product of those two vectors, we would have 0, minus 2 plus 2, which is 0. So since the dot product of any distinct pair of vectors is 0, that means they are all orthogonal to one another. So the set of vectors, u1, u2, u3, is an orthogonal set. All right. Now the next theorem, theorem 6.4 from your textbook, gives us a little information about orthogonal sets. In particular, if S is a set of vectors u1 through up, and this is an orthogonal set of non-zero vectors in Rn, then that set S is linearly independent and therefore is a basis for the subspace spanned by that set. So in order to show that a set of vectors is linearly independent, we would consider some linear combination of those vectors, say c1 u1 plus c2 u2 up through cp up. We'd set that equal to the 0 vector. And in order to show that these vectors are linearly independent, we need to show that the only solution of this is for C1 up through CP to all be 0. So let's see how we can show that using the orthogonality of these vectors. So if we were to take the dot product of the 0 vector with, say, u1, we know that we would get the constant 0 because the 0 vector has all 0 entries, so its dot product with any vector is 0. But now we were writing the 0 vector as this linear combination of c1 u1 up through cp up. So we're taking this dot product with the vector u1. Now using properties of the dot product, if I have a linear combination and I'm taking a dot product with a vector u1, that's the same as the linear combination of the dot products. So I can take c1 u1 dot u1 plus c2 u2 dot u1 up through cp up dot u1. And this is the same as taking the constant c1 times the dot product of u1 with itself, plus c2 times the dot product of u1 with u2 up through CP times the dot product of UP with U1. But now recall that these vectors, U1 through UP, formed an orthogonal set. So the dot product of any two distinct vectors must be 0. So taking here the dot product of U1 with UP, we have 0, along with the all of the other dot products for these middle terms. Say the dot product of U1 with U2, and so on. So the only term that I'm left with is this first term, C1 times the dot product of U1 with itself. Now, since the vector U1 is a non-zero vector, because remember in the statement of this theorem we were taking a non-zero set of vectors, or a set of non-zero vectors, so that means that the dot product of U1 with itself cannot equal to 0. Remember, the only vector whose dot product with itself is equal to 0 is the 0 vector. And so we can say C1 must be 0. So the only way this product of two terms can equal 0 is if one of these factors is 0, and we've shown that the dot product of U1 with itself is non-zero, so by default the constant C1 must be 0. Now similarly, we can show that all of the other constants, C2 up through CP, are all 0 by taking the 0 vector dot product with any of these other vectors, say U sub j. So since all of our constants are 0, that means that the set of vectors S is linearly independent. Okay. So in the next part of our section, we're going to talk about something called an orthogonal basis. So let's define it. We would say an orthogonal basis for a subspace W of Rn is a basis for that subspace W that is also an orthogonal set. So the following theorem will illustrate why an orthogonal basis is much nicer than other bases. And it has to do with the way that we can find the weights for a linear combination of those basis vectors. So let's consider the following. Suppose that U1 through UP is an orthogonal basis for a subspace W of Rn. So for any y within that subspace, if we're expressing y as a linear combination of these basis vectors, U1 through UP, the weights in this linear combination are given by the following equation. So the jth weight is the dot product of our vector y with the jth vector from our basis divided by the dot product of uj with itself. So this gives us an easy way to determine these weights directly from the given vectors. So let's see if we can establish this result. So I'll mention here that as with the previous proof, the one that we had just completed, the orthogonality of our set of vectors, U1 through UP, can be used to show that the dot product of our vector y with U1 is equal to, well, since y is in W, it can be a linear combination of these basis vectors, U1 up through UP. So taking the dot product with u1 and using the orthogonality, we're left with simply c1 times the dot product of u1 with itself, as we had shown in that previous theorem. So since the dot product of u1 with itself is non-zero, because u1 is not zero, since it is an element of a basis. We know any set of vectors that forms a basis has to be linearly independent, so it can't contain the zero vector. So since this dot product is non-zero, we have C1 is equal to the dot product of y with u1 divided by the dot product of u1 with itself. Now, similarly, if we were to compute the dot product of y with any other vector, say uj, and go through the same process, we have c sub j is equal to the dot product of y with u sub j divided by the dot product of u sub j with itself. All right. So let's look at an example working with an orthogonal basis. So in this next problem, we're supposed to show that the set of vectors u1 and u2, which are given here, is an orthogonal basis for R2, and then express the vector x, given here, as a linear combination of u1 and u2. So in the first part of this problem, we have to show that this set is an orthogonal basis for R2. So first, let's show that these two vectors are orthogonal by looking at their dot product. So taking u1 dot u2, we have a -6 plus 6, which is 0. So since this dot product is 0, the set of vectors u1, u2 is an orthogonal set. Now we need to show that these two vectors form a basis for R2. So here, if we have two vectors which are linearly independent, then they must span R2. So it's clear that these two vectors, u1 and u2, are linearly independent because they are not scalar multiples of one another. So we can say clearly u1 and u2 are linearly independent and therefore span R2. So we have a basis for R2 then, which is an orthogonal set. So we can say thus our set of vectors u1, u2 is an orthogonal basis for R2. So that was the first part of this problem. Now we're supposed to then show that the vector x, which is -6, 3, can be written as a linear combination of u1 and u2, so let's find the weights. So making use of theorem 6.5, let us compute the following. Let's compute the dot product of x with u1, which is equal to, let's see, -18 plus 3, so -15. Let's take the dot product of x with u2, which would be 12 plus 18, or 30. And then we need the dot product of u1 with itself, which would be equal to 9 plus 1, or 10. And the dot product of u2 with itself is equal to 4 plus 36, so 40 here. Okay, so now, by making use of theorem 5.6, or 6.5, we have the vector x can be written as a linear combination c1 u1 plus c2 u2, where the weight c1 is given by the dot product of x with u1, which was negative 15, divided by the dot product of u1 with itself. So I've got negative 15 over 10 times u1, plus the second weight, c2, was given by the dot product of x with u2, which was 30, divided by the product of u2 with itself. So here we would have 30 over 40 times u2, or simplifying a little bit, we have negative 3 halves u1 plus 3/4 u2. All right. So let's consider another example, somewhat similar, but now involving 3 vectors. So in this example, as with the last one, we're supposed to show that the set of vectors is an orthogonal basis for R3, where our vectors are given here, and then express the given vector x as a linear combination of these 3 basis vectors. So as with the last example, to show that this set is an orthogonal basis, we first need to show that it's an orthogonal set. So let's say first, let us compute our dot products of these 2 vectors, or any pair of vectors. Say u1 with u2, which would be 6 minus 6 plus 0, which is 0. Taking the dot product of u1 with u3, we have 3 minus 3 plus 0, which is 0. And then lastly, taking the dot product of u2 and u3, we would have 2 plus 2 minus 4, which is 0. So we've established that the set of vectors u1, u2, u3 is an orthogonal set. Now, to show that this is an orthogonal basis for R3, we have to show that this set of 3 vectors is a basis for R3. So let's say the following. To show that our set of vectors u1, u2, u3 is a basis for R3, we can consider the following. So to show that a set of 3 vectors in R3 forms a basis, we could consider the determinant of the matrix which has these vectors as its columns. So that is the determinant of the matrix whose first column is 3, negative 3, 0. Second column is 2, 2, negative 1, and third column is 1, 1, 4. So using a cofactor expansion down the first column, I would have 3 times 8 minus a negative 1, or 8 plus 1, then plus 3 times 8 minus negative 1, or 8 plus 1, plus 0. So this is 27 plus 27, or 54, which is certainly non-zero. So that means that the matrix which we're taking the determinant of is invertible. And by the invertible matrix theorem, these column vectors are linearly independent and span R3. Therefore, they form a basis for R3. So we can say that our set of vectors u1, u2, u3 forms a basis for R3. So we have an orthogonal set, which is also a basis, so we have an orthogonal basis for R3. Now, the last part of this problem is to express the given vector x as a linear combination of these three vectors. So to do that, let us compute some quantities needed for theorem 6.5, starting with the dot product of x with the vector u1. So let's see, we've got 15 plus 9 plus 0 is 24. The dot product of x with u2 is equal to 10 minus 6 minus 1, so 3. And the dot product of x with u3 is 5 minus 3 plus 4, which leaves us with 6. And then we also need the dot product of u1 with itself, which would be 9 plus 9 plus 0, so 18. The dot product of u2 with itself, which would be 4 plus 4 plus 1, or 9. And the dot product of u3 with itself, which is 1 plus 1 plus 16, so 18. So now, by making use of theorem 6.5, we have the vector x can be written as a linear combination of u1, u2, u3, where the weights are given by the following. So for our weight c1, we take the dot product of x with u1 divided by the dot product of u1 with itself. So that would be 24 over 18 for the weight of u1. Then we add our second weight would be the dot product of x with u2 divided by the dot product of u2 with itself, so 3 over 9 u2. Plus for our third weight, we would have the dot product of x with u3 divided by the dot product of u3 with itself, so 6 over 18 u3. Or simplifying our weights a little bit, we would have 4/3 u1 plus 1/3 u2 plus 1/3 u3. So theorem 6.5 is illustrating the usefulness of an orthogonal basis as opposed to just an ordinary basis. And the main point is that it's easy to compute the weights needed to build an arbitrary vector y from an orthogonal basis. So if this basis were not orthogonal, if we couldn't use theorem 6.5, we would have to solve a system of linear equations in order to find our weights here. So we would have to, in this example, write out c1 u1 plus c2 u2 plus c3 u3, set that equal to x, express that system as an augmented matrix, perform row reduction, and then we would get our weights. But this process of just computing these dot products is much easier. Now in the next part of this section, we'll talk about what's called an orthogonal projection. So let's consider the following motivation. Suppose that we have a non-zero vector u in Rn, and our problem of interest will be to decompose a given vector y in Rn as the sum of two vectors, one of them being a multiple of the vector u, and the other being orthogonal to u. So that is, we want to write a vector y as the sum of two vectors, let's call them y hat and z, where y hat is some scalar multiple of the vector u, for some scalar alpha, and z is a vector which is orthogonal to u. So to illustrate this problem, let's consider the following. Say that we have an R in some vector, I'm going to call it y, and I have a vector, let's call it u, some non-zero vector in Rn. So if I draw the representations of these vectors as position vectors, so their initial point is the origin or the 0 vector, my goal is to decompose y into the sum of two vectors, where one component is a scalar multiple of the vector u. So if I were to take the vector alpha times u, maybe that represents the first component of my vector y, and then its second component would be some vector which is orthogonal to the vector u, so that they intersect at a 90-degree angle, or they're perpendicular. And this would be my vector z. So we can see from our equation here that if we're able to do this, z could be expressed as the vector y minus y hat. So this is my goal, is to decompose an arbitrary vector y into the sum of two vectors, one which is a scalar multiple of a given vector, and the other being orthogonal to that given vector. So if we're trying to accomplish this, given any scalar value alpha, let's let z be equal to y minus alpha times u. So here, solving for z, we had z was y minus y hat, where y hat is alpha times u. So z is y minus alpha u. And we want this vector z, which is y minus y hat, to be orthogonal to the given vector u. So that is accomplished if and only if the dot product of those two vectors is 0. So that is if the dot product of y and y hat, which is a scalar multiple of u, with the vector u is 0. So using the properties of the dot product, this is the same as taking the dot product of y with u minus alpha u dot product with u, or this is the same as taking the dot product of y with u minus the scalar alpha times the dot product of u with itself. Now, solving, we would have alpha times the dot product of u with itself is equal to the dot product of y with u, and so the scalar alpha would be the dot product of y with u divided by the dot product of u with itself. So once we have the scalar alpha, we have our vector y hat. It's alpha times u. So our vector y hat, which is alpha u, is given by the dot product of y with u over the dot product of u with itself, which was our scalar alpha, times u itself. So what we've established is the following. We can express y as the sum of two vectors, y hat and z, with z being orthogonal to a non-zero vector u, if and only if alpha is defined as this ratio of our dot products and y hat is defined as alpha times u. So this vector, y hat, is referred to as the orthogonal projection of y onto u. And the vector z, which is equal to y minus y hat, is called the component of y orthogonal to u. All right. So here in our illustration, this first vector is our y hat vector, and the vector orthogonal to that is this vector z. So z is referred to as the component of y orthogonal to the vector u, and the orthogonal projection of y onto u is the vector y hat. Now, in the event that we have some scalar, c, which is a non-zero scalar, and we're considering replacing the vector u by a scalar multiple of u in the definition of y hat, then the orthogonal projection of y onto any scalar multiple of u is exactly the same as the orthogonal projection of y onto just u itself. So this projection is determined by the subspace L spanned by u, which we can think of as a line through the origin and the vector u. And this vector y hat is denoted as follows. It's the projection of y onto L, or the orthogonal projection of y onto the line L, defined by that vector. So here y hat, or the orthogonal projection of y onto L, is this vector y dot u divided by the dot product of u with itself times the vector u. So what we're saying here is if we have a given vector u and we consider any scalar multiple of that vector, so if we have all positive scalar multiples, we get vectors u extending infinitely far in this direction, or if we take negative scalar multiples of u, we get vectors extending infinitely far in the opposite direction. So this is a line L through the origin in the direction of u. It forms a subspace of Rn, and the orthogonal projection of our vector y onto that line is this exact same red vector shown here. Okay. So let's look at some examples. In this next problem, we're asked for the orthogonal projection of y, which is 2, 6, onto the vector u, which is 7, 1. And then we want to write y as the sum of two orthogonal vectors, where one is in the span of u and the other being orthogonal to u. So in order to compute our orthogonal projection, we need to make use of the formula that we just derived. So we need to compute a few things. First, the dot product of y with u, which would be equal to 14 plus 6, or 20, and the dot product of u with itself, which would be 49 plus 1, or 50. So the orthogonal projection of the vector y onto u is the vector which we were calling y hat, and it's found by taking the dot product of y with u, which was 20, divided by the dot product of u with itself, which was 50, times the vector u. Or in other words, 2/5 of the vector u. So that's 2/5 of u was 7, 1. So we would have the vector 14/5 and 2/5. All right. Now we also need the component. So we could say the component of y orthogonal to u is the vector z, which is defined as y minus y hat. So that is y, which was 2, 6, minus y hat, which we just found to be 14 fifths, 2 fifths. So let's see. For our first component, we had 2 or 10 fifths minus 14 fifths gives us negative 4 fifths. And our second component, we had 6 or 30 fifths minus 2 fifths gives us 28 fifths. So our vector y can be written as the sum of y hat, which we found to be 14 fifths, 2 fifths, and z, the component of y orthogonal to u, which was negative 4 fifths, 28 fifths. And as sort of a way to check ourselves here, we need to make sure, or we can make sure that the vectors y hat and z are orthogonal. So note that if we take the dot product of the orthogonal projection of y onto v with the orthogonal component, then we would have the following. We've got, let's see, a negative 56 over 25 plus 56 over 25, which is indeed 0. So those vectors are indeed orthogonal to one another. Okay. So let's consider a similar problem. Suppose that we have two vectors, y and u, in the plane, and we're asked to find the distance from y to the line through u and the origin. So let's start by visualizing our problem here. So we've got the vectors y. So y was negative 3, 9. So let's sketch that vector here. We've got the following for y. And then we had a vector u, which was 1, 2. So its representation here. And we're considering the line through u and the origin. So the line through u and the origin would be this line shown here. Let's call that line L. And then U2 was this, or U was the vector giving us that line. So the distance from y to this line would be this distance shown here in blue, which would be the magnitude of the orthogonal complement of y to the vector u. So if I were to draw that same vector here, we can see that this vector is z, the orthogonal complement of y to the vector u. So we can say that here our distance would be the magnitude of our orthogonal complement z. So to find that orthogonal complement, we need to calculate a few things. So let's start by computing the following, starting with the dot product of y with u, which here is negative 3 plus 18, so 15, and the dot product of u with itself, which would be 1 plus 4, or 5. So then the orthogonal projection of y onto this line, that is the projection of y onto L, is the ratio 15/5 times u, or 3 times u. So let's calculate that value. We have 3 times u, which was the vector 1, 2. So we have the vector 3, 6. And from here we can find our vector z that we need. Z is defined as y minus y hat. So here we have y, which was -3, 9, minus y hat, which was 3, 6. So we're left with the vector -6, 3. So our distance that we're interested in from the vector y to L is the magnitude of this vector z. So that is the square root of the sum of the squares of the components of z. So 6 squared, or -6 squared is 36, and then plus 3 squared is 9. So I'm left with the square root of 45, or this is 9 times 5, so taking the square root, we have 3 root 5 for the distance from our vector y to the line passing through u. So in the last part of this section, we're going to talk about something known as orthonormal sets. So let's define this. We would say that a set of vectors u1 through up is an orthonormal set if it is an orthogonal set of unit vectors. So any orthogonal set of vectors which have length 1 is an orthonormal set. And if we have a subspace W spanned by an orthonormal set, then that set is referred to as an orthonormal basis for the space W. Since that set is automatically linearly independent by using theorem 6.4. Recall that theorem said any orthogonal set of non-zero vectors must be linearly independent. So the simplest example for an orthonormal set would be the standard basis of unit vectors e1 through en for Rn. So we know that those are all orthogonal and they are unit vectors. So this is a simple example of an orthonormal basis. So in our next example, let's consider the problem of showing that a set of vectors forms an orthonormal basis for some space. So here we're supposed to show that v1, v2, v3 is an orthonormal basis for R3, where we're given these 3 vectors. So first we have to show that they are an orthogonal set. And to show that these are an orthogonal set, we will compute the dot product of any pair of these vectors. So say v1 dot product with v2 gives us 1 over square root of 2 times square root of 18 would be root 36, or 1/6. Plus 0, and then minus 1 over root 36, which is 0. Taking the dot product of v1 and v3, we have -2 over 3 root 18 plus 4 over 3 root 18. And then minus 2 over 3 root 18, which is 0. And then taking the dot product of v2 and v3, we have -2 over 3 root 2 plus 0 plus 2 over 3 root 2, which is 0. So this set of vectors is an orthogonal set. Now to show that this is an orthonormal set, we need to show that each of these vectors is a unit vector. So let's say also if we calculate the dot product of v1 with itself, we would have 1/18 plus 16/18 plus 1/18. So that is 18/18 or 1. The dot product of v2 with itself is equal to 1/2 plus 0 plus 1/2, which is 1. And the dot product of v3 with itself is 4/9 plus 1/9 plus 4/9, so that is 9/9 or 1. So this shows that the vectors v1, v2, and v3 are unit vectors. Now, why does that result hold? Well, recall that the dot product of a vector with itself is the magnitude of that vector squared. So if the dot product of a vector with itself is 1, that means the length of that vector squared is 1, and we have to have a positive length for a vector, so it would have unit length. So we've shown that the set v1, v2, and v3 is an orthonormal set. So the last thing we need is to show that these vectors form a basis for R3. So if you consider the matrix which has these three vectors as its columns and calculate the determinant of that matrix, we see that it's non-zero. So here we'll just say since the set is linearly independent, it is an orthonormal basis for R3. All right. So the last part of this section has to deal with a particular type of matrix. So those are matrices whose columns form an orthonormal set. So these sort of matrices have some important applications that you might see later in your career if you're doing engineering or physics or some sort of computer programming and in approximation. So the following two theorems give some properties for these sorts of matrices. Theorem 6.6 says that an m by n matrix U has orthonormal columns if and only if the transpose of U multiplied by U is equal to the identity matrix. So that is if the inverse of U is equal to its transpose. Now, Theorem 6.7 says if we have a matrix U, which is an m by n matrix with orthonormal columns, and we have two vectors x and y in Rn, a few properties hold. Property A says that the length of U times x is the same as the length of x. The dot product of the vectors ux and uy is equal to the dot product of x and y. And the dot product of ux and uy is equal to 0 if and only if the dot product of x and y is 0. So in particular, properties A and C say that if we're considering a linear mapping where x is mapped to u times x, that mapping preserves length, since the magnitude of, or the length of u times x is the same as the length of x, and it preserves orthogonality. So if the dot product of two vectors x and y is 0, that means they're orthogonal. So if we look at the images of those vectors under the transformation U, those two images would also have a zero dot product, so they would be orthogonal. So in our last example here, we are given a matrix U, which is the following, and X is this vector 3 root 5. So we can notice that the two columns of the matrix U are orthogonal, and they are unit vectors, so they form an orthonormal set. Now, in part A, we're supposed to verify the result from theorem 6.6 that U transpose times U is equal to I. So considering the product U transpose times U, U transpose will be a 2 by 3 matrix where our first row is negative 2/3, 1/3, 2/3. And our second row is 1 over root 5, 2 over root 5, and 0. And we're multiplying by U, which is the 3 by 2 matrix, whose first column is negative 2/3, 1/3, 2/3. And the second column is 1 over root 5, 2 over root 5, 0. So this product will give us a 2 by 2 matrix where the first row, first column entry would be found by taking the first row and first column and taking their dot product. So we would have a 4/9 plus 1/9 plus 4/9, which is 9/9 or 1. Our entry in the first row, second column is the dot product of these two vectors, but notice that those are the two rows of the matrix U, which were orthonormal. So their dot product must be 0. Now taking the second row, first column vectors and taking the dot product, well, we have the dot product of the same two vectors that we had for the first row, second column. So again, we get 0. And then lastly, taking the dot product of the second row and second column, we have 1/5 plus 4/5 plus 0, which would be 5/5 or 1. So we do have the identity matrix here. And in part B, we're supposed to verify that the length of U times X is equal to the length of X. So let us start by calculating U times X. So that is the matrix negative 2/3, 1 over root 5, 1/3, 2 over root 5, and 2/3, 0. Times X, which is 3 root 5. So we get back a 3 by 1 column vector where our first row, first column, is given by negative 2 plus 1, so negative 1. Our second row would be 1 plus 2, so 3. And our third row is 2 plus 0, so 2. And now the length of this vector, U times X, is the square root of the sum of the squares of its components. So negative 1 squared is 1, plus 3 squared is 9, and then 2 squared is 4. So we have root 14. And then let's see if that's the same as the length of X. So we're taking the square root of the sum of the squares of its components. So 3 squared is 9, plus the square root of 5 squared is 5. So again, we have root 14, so we see that these values are indeed